Welcome to The Explainer. So, today we're exploring a seriously fascinating parallel, which is how human learning and our own human sense of self actually mirror the architecture of modern artificial intelligence. We're going on a journey from the deep philosophy of the human mind all the way down into the dense mathematics of neural networks. Okay, let's dive into this. Here is our roadmap for today. Section 1, the illusion of knowledge. Section 2, constructing the human self. Section 3, inside transformer AI architecture. Section 4, teaching machines to see. And finally, Section 5, aligning and securing AI. Section 1, the illusion of knowledge. Let's kick things off with a pretty fundamental question. What does it actually mean to know? And I mean completely understand something. Imagine someone just walked right up to you right now and said, "Explain yourself." Could you do it? Could you truly articulate your own inner workings, your thoughts, and your decision-making processes to another person? It's a lot harder than it sounds, right? There's this brilliant grammatical quirk that perfectly illustrates the challenge here. Just think about the difference between saying, "explain me," and "explain to me." If you write a letter saying, "Dear Dr. Freud, please explain me," you're asking someone to unpack your very identity, to break down the massive, complex system that is you. But if a kid holds up a drawing and you say, "explain to me what it is," you are asking them to break down a specific concept. Both require taking something highly complex and translating it into simple, understandable terms, because ultimately, communication requires breaking things down. Listen closely to how the philosopher Mortimer Adler put it. He said, "The person who says he knows what he thinks but cannot express it usually does not know what he thinks. True comprehension absolutely requires the ability to express ideas simply. If you can't strip away the jargon and explain the core essence of a topic, well, your knowledge is likely just an illusion." And this brings us to the Feynman technique. It's an incredibly effective 4-step method for accelerated learning. Step 1, choose a concept and study it. Step 2, teach it to someone else or, at least pretend to. Step 3 is the absolutely crucial one. Identify and fill your knowledge gaps when you inevitably stumble. And you will stumble, for sure. But that stumbling, that friction, that's where the actual learning occurs, because it forces you to go back and figure out exactly what you missed. And finally, step 4, simplify even further by using analogies. For example, if you're explaining the programming concept of recursion, you don't use dense code jargon, you use the analogy of Russian nesting dolls, opening one doll to reveal a smaller one inside until you hit the smallest doll, the base case. Identifying gaps and using analogies is how we securely connect new ideas to our prior knowledge. Section 2, constructing the human self. So if that's how we learn about the outside world, how do we actually learn about and construct our internal world? Now, what's really interesting about this concept is that philosophers and cognitive scientists break our minimal self down into two distinct senses. First, the sense of agency. That's the feeling that I am the one causing an action. Second, the sense of ownership, the feeling that I am the one undergoing an experience. Our brains literally use neurological forward and feedback comparators to figure this out. If I reach for a cup of coffee, my brain predicts the movement and matches it with sensory feedback, telling me, yes, I initiated this, and yes, it's my arm moving. When these two align, we have a healthy minimal sense of self. Interestingly, certain neurological conditions can actually sever these two senses, making people feel like their arm is moving completely on its own, which beautifully proves these are distinct, separate systems operating in the brain. But humans don't just exist in the momentary minimal self. We have what's called the narrative self. Because we have language and episodic memory, we constantly weave together past memories and future plans to create a continuous story. Think about the story you tell yourself when you look in the mirror. That's your narrative gravity at work. We spin stories that give our identity a coherent, understandable structure over time. Section 3, inside transformer AI architecture. Now that we've established this baseline of human learning and self-construction, let's pivot. How do we structure machines to process data, learn, and actually understand context? We use transformers. To understand machine comprehension, we have to look at the attention matrix. Much like how human attention focuses on specific contexts to make sense of a sentence, a transformer model uses a mechanism called self-attention. It mathematically weights the relevance of different data points across a sequence. Let's say the model reads the word bank. Self-attention calculates the mathematical relationships with all the surrounding words to figure out if it's a riverbank or a financial bank. Take a moment to really digest that. It aggregates this information independently, dynamically generating these attention maps based entirely on the input data itself. This builds into a complete structure known as the full transformer block. It interleaves that multi-head self-attention, or MHSA, with multi-layer perceptrons, or MLPs. You can kind of think of multi-layer perceptrons as a series of increasingly complex filters that refine the data. But just as importantly, the architecture uses something called token normalization, often layer norm. Think of this as a totally critical stabilizing mechanism. As the model repeatedly applies nonlinear transformations across hundreds of layers to refine its understanding, normalization stops the numerical features from blowing up in magnitude. It essentially keeps the model's learning grounded and perfectly stable.
Section 4. Teaching machines to see. Okay, so we've talked a lot about sequences of words, but how do these models ingest and interact with the visual world?
Vision transformers process an image by breaking it up into a grid of tiny patches. And then they use a matrix to mathematically map each patch into an abstract vector. Now, this patch-making process, this is actually exactly how modern facial recognition works. The AI doesn't see a nose or eyes like we do. No, it converts patches of a face into abstract mathematical vectors, measuring the exact geometric distances between features to create a unique mathematical signature for a specific identity. It is highly mathematical and completely disembodied. But contrast that abstract math with a physical embodied approach, like Tani's vision-based robot. This robot was designed to integrate bottom-up sensory motor inputs with top-down predictive models. When the robot encounters an inconsistency between what it predicts and what its cameras actually see, it enters a state of conflict. To resolve this, it has to take its own current state into account. In a really primitive way, it creates a short-term, momentary self to arbitrate that conflict. It's a fascinating robotic mirror to our own minimal self.
Section 5. Aligning and securing AI. So, the crucial point is, as these models gain the ability to process text, audio, and detailed visual data, the risks scale exponentially. So how do we actually test, regulate, and secure these powerful machine minds?
Major tech organizations rely on standardized frameworks, like the standard NIST AI Risk Management Framework. It breaks down into 4 key functions: govern, map, measure, and manage. This structured approach ensures that when a company deploys a generative AI system, they are systematically identifying potential vulnerabilities and managing risks before they ever hit the real world. A massive part of this process is red teaming, which is essentially acting like a strict teacher, deliberately looking for gaps in a student's knowledge. Take Microsoft's Phi models, for example. When they red teamed the Phi 3 vision model, they aggressively probed its facial recognition capabilities. Because we know the model maps faces into unique mathematical vectors, red teamers test if the model can be tricked into cross-referencing those vectors with public data to inappropriately identify individuals, or, to infer sensitive private attributes just from an image of a person. It is a massive privacy risk, which is exactly why developers deliberately attack the model to find these gaps. As the models evolved to Phi 3.5, red teamers tested multilingual bypasses using obscure scripts. By Phi 4, which introduced audio, they tested the model against persuasive audio attacks and its tendency to infer personality traits or origins from users' voice. By playing the attacker, developers find the weak points and fix the vulnerabilities. Which brings us to our final thought. We use the Feynman technique to ensure we understand complex concepts. We weave narratives to understand our own identity. Now, we are building incredibly complex multimodal machines that can read, hear, and see the world, including recognizing our own faces. But as we look into this technological mirror, we have to ask ourselves, we are building machines that understand the world, but as their architectures grow ever more complex, do we truly understand them? Thank you for joining me on this explainer. I really hope this sparked some curiosity for you to explore further.